I'll be talking about the processing for latex condoms. How do they get such uniform, thin thickness and such an exact shape? Here we have a worker that has just harvested natural latex, and what he's doing is straining it to get all non-natural latex particles out. And here's an endless chain of glass molds. Here they are coming down. What they're going to do is dip into the latex bath and become immersed in the latex. Latex has a melting point right around room temperature, so there really isn't much of a temperature gradient here. And as you can see, they're slowly pulled out, and when the glass molds are pulled out, they come out with a very uniform coating of latex. And later on, they're going to go through a baking process to remove all the water and then get dipped a second time. So there are two main engineering problems associated with this process. The first occurs with the horizontal movement through the bath. What we want is laminar flow so that there's uniform contact pressure between the latex and the glass mold all around. That way it's not thicker in the front and thinner in the back. We want a uniform thickness of these condoms, but we also want to maximize the horizontal velocity. The second engineering problem has to do with the upward draw of the mold out of the latex bath. We want to draw it out as fast as possible so we can process more condoms per hour. But at the same time, we want to maintain a uniform, specified thinness of condoms. Let's tackle the problem of laminar flow. There's two main assumptions we made. One, the laminar flow is in fact necessary for uniform contact, and the other that our glass mold is essentially a smooth cylinder passing through this bath. So Reynolds number is a measurement of whether or not the flow will be turbulent or laminar. And we want laminar, which just means smooth flow right around the cylinder. And so from this graph of Reynolds number versus drag coefficient, we know that the flow will be laminar in approximately the linear regime of the Reynolds number. And so I found a cutoff of about Reynolds number of 8, and this gave us a maximum horizontal velocity of 24 millimeters per second. Just from an offhand calculation from the video, I kind of got that I saw it move 2 times the diameter of one of those cylinders in about a second, which gives me an estimated velocity of about 100 millimeters per second, assuming that the width of those condoms is 50 millimeters as listed on the manufacturer's website. And so this is about 4 times our velocity. So one explanation could be that perhaps through experimental testing, maybe they needed a higher run of condoms. A turbulent flow up to a critical Reynolds number of about 32 still allows for uniform interaction of the liquid latex with the glass substrate. Now let's look into the problem of maximizing upward draw velocity. I've chosen to ignore evaporation and vertical drainage, and what we're left with are 3 relevant forces: gravity, viscous drag from the glass pulling the liquid upward, and surface tension between the glass and the latex. So, from a paper by Scriven, what I found is an equation that gives me the velocity in terms of the desired thickness, or vice versa. I've chosen a thickness that is about 2.5 times the thickness of a final condom as listed on the manufacturer's website, because we have to account for this actual solid fraction of latex that remains after baking occurs later. And what this gives us is a maximum vertical velocity of about 7 millimeters per second, which also gives us uniform thickness throughout the process. Once again, I used the video as a benchmark against which to measure my estimation, and I got that it drew upward at about a velocity of half a diameter every 2.5 seconds, or about 10 millimeters per second, which is remarkably close to my estimation. But of course there's room for error based on the exact values of the materials properties used in the calculation. And that's how condoms are made. Just goes to show, all these physical relations everyone learns in school, with about fluid flow or heat transfer, can all be used to design a factory, predict profitability or quotas, and whether or not you can upgrade existing factories when new materials become available.